Welcome to the deep dive. Today we're tackling something really vital for anyone aiming for that top-tier precision in manufacturing: centerless grinding.
Hmm.
You've sent over a really interesting stack of information, and our job here is, well, to cut through it all and pull out the critical insights, the things that take a good centerless grinding setup to an exceptional one.
Right.
You want to arm you with actionable knowledge, basically, to help sidestep those common headaches and consistently hit that premium quality finish.
Exactly. You've given us a fantastic starting point, and what we're going to do is really dig into the nitty-gritty of how all the different parts of this process, fit together for peak performance.
Okay.
We'll be looking at everything. I mean, from making that crucial first decision about which grinding wheel to use,
Yeah.
right through to setting up those essential maintenance routines that, well, keep these machines running smoothly.
Okay, let's dive right in then. Something that might seem obvious, but your sources really hammer home its importance: the grinding wheel itself.
Yeah.
It's clear the right wheel isn't just some minor detail. It fundamentally shapes the whole operation. We're talking surface finish, how fast you remove material,
Right. The removal rate.
how long the wheel lasts, and, the bottom line, the cost.
Absolutely. It's not just about grabbing any old wheel off the shelf. It's a very deliberate choice, and it hinges on several factors that are all connected.
Like what?
Well, the abrasive itself is huge. Are we talking conventional abrasives, or are we stepping up to super hard materials like CBN cubic boron nitride or diamond?
Okay.
Then you've got the grain size, the size of those abrasive bits, the bond that holds it all together, and of course the hardness of the wheel. Each of these really impacts how the grinding goes.
And the info you shared gives examples like super abrasives are amazing for really tough metals. They hold their edge forever, it seems,
For a very long time, yeah.
which obviously means less downtime changing wheels. But like you'd expect, they cost more upfront.
They do. It's that classic cost-benefit calculation, isn't it? It is. And it's about finding that sweet spot for what you're doing, the specific materials you're working with.
Right.
You also see a clear difference made between coarser grains, great for roughing, taking off lots of material quickly.
Get the bulk off.
Exactly. And then the much finer grains, which you need to get that really polished, almost mirror-like finish. But, and this is critical, something your sources really emphasize, even the best wheel, the most advanced, most expensive one, it's not going to give you top results if the machine itself isn't set up right.
Okay. Which leads us perfectly into that next big area.
Yeah.
Those key setup parameters. It sounds like getting these dialed in is just foundational.
Absolutely.
And it's the difference between smooth sailing and, well, a whole mess of problems, chatter marks, parts coming out not quite round.
Precisely. Think of the machine setup as the foundation, literally. If that's shaky, everything you build on top precision quality, it's going to suffer.
Makes sense.
And there are quite a few parameters, all interconnected, that need careful attention. We've already mentioned the grinding wheel, but just as vital is the regulating wheel.
The other wheel.
Yeah, sometimes it gets a bit overlooked, but it's critical. It controls how fast the workpiece rotates and how fast it feeds through the grinder.
And, just like the grinding wheel, the regulating wheel has its own specs to consider, doesn't it? Your notes mention abrasive type.
Mm-hmm.
So, aluminum oxide, silicon carbide, maybe for softer stuff, or again, CBN or diamond for those really hard alloys.
Right.
And then grain size, bond type, vitrified, resinoid, and wheel hardness. It sounds like similar considerations, but for a different job.
Exactly right. The grinding wheel does the cutting, removing material. The regulating wheel ensures consistent contact, guiding the workpiece steadily.
Okay.
Then there's the work rest blade. We'll dig into that more soon. But its material, its height, and crucially, its angle are all super important factors.
Got it. Angle.
And we can't forget wheel speeds. You need the right balance. The grinding wheel's surface speed for good cutting action, and the regulating wheel speed for consistent rotation of the part.
And coolant. Let's not skip that. The sources you send are really strong on this.
Oh, yeah.
It's definitely not optional. It's essential for cooling, flushing away the grit, the swarf, and lubrication. Skimping here sounds like a recipe for disaster.
It really is. Not enough coolant or bad coolant, and you get thermal damage, bad finish, a whole cascade of problems.
Right.
Then there's the basic choice of how you grind. Are you doing Thrufeed or Infeed? That depends mostly on the part's shape.
We'll get to that difference too.
Yeah. And of course, proper machine alignment and keeping the wheels dressed, meaning trued and sharpened, are critical for accuracy. Modern CNC helps a lot. But the skill of an experienced operator making those little fine-tuning tweaks, Still incredibly valuable.
Okay, you mentioned we'd circle back to it. Let's really focus on this work rest blade.
Yeah.
It looks simple, but the sources make it sound like much more than just a shelf for the part.
Oh, definitely. It's described as this critical third point of contact.
Good point. Okay.
Exactly. It's not just passive support. It actively helps stabilize the part during grinding, which directly impacts the final quality and the angle of its top surface. That's particularly important.
Why the angle?
It directly affects how much pressure pushes the workpiece against the regulating wheel.
Okay, so the info explains that a steeper angle, say around 30 degrees, is often better for narrower wheels or smaller diameter parts. The idea is more pressure gives better rotation control, maybe better roundness.
Correct. That pressure helps keep things rotating smoothly.
But there's a catch. You might get vibrations if it's too steep or too much pressure.
That's the trade-off. It's a really important nuance. That extra pressure is good for controlling small parts, but it can cause problems like chatter marks on bigger or more flexible parts.
Oh, okay.
So that's where a flatter angle usually comes in, maybe 20 to 25 degrees.
Flatter for bigger parts.
Generally, yes. Or for wider wheels. It reduces that downward force, minimizes vibration, improves stability, and ultimately helps get better roundness and finish on those larger workpieces.
It really drives home that there's no single magic number here, is there?
Not at all.
Finding the best angle is a balancing act. Depends on the wheel width, the part's diameter, the material.
All of the above.
And it seems obvious, but a worn blade or one set at the wrong angle, that's just asking for trouble. Geometric errors, bad finish.
Absolutely. Leads right to those problems we talked about.
So checking and adjusting that blade regularly sounds non-negotiable for consistent quality.
It really is a small detail with a surprisingly big impact on the outcome.
Okay.
Now let's maybe shift gears a bit and talk about the two main ways to do centerless grinding. Infeed and Thrufeed.
Right. To someone new, they might sound similar, but they're really distinct approaches for different kinds of parts.
Very distinct. So infeed grinding, sometimes called plunge grinding,
Plunge, okay.
is what you typically use when the part isn't just a simple, straight cylinder. Your notes mention things like grinding the shanks on headed bolts.
Where the head would get in the way of through feeding.
Exactly. Or making parts with multiple diameters at once, using a specially shaped wheel. Even tapered parts or complex shapes like hourglass forms. The key thing is the grinding wheel moves in towards the part, which stays pretty much put axially.
So the part isn't traveling along its length.
Correct. You position the workpiece on the rest blade, often using an end stop for precise location.
Okay.
And then the grinding wheel feeds radially inward, plunging into the material to create the shape. No continuous axial movement during the grind cycle itself.
Got it. And then there's through feed grinding. The name kind of gives it away. Parts feed through the machine.
Right. Continuously fed, usually straight cylindrical parts, between the grinding wheel and the regulating wheel.
And what's interesting is you mentioned the regulating wheel is tilted slightly.
Yes, deliberately tilted at a small angle.
And that tilt is what pulls the part through.
Exactly. It generates the axial force needed to draw the workpiece steadily through the grinding zone. That slight angle is the key mechanism.
Fascinating.
Thrufeed is really the workhorse for high-volume production of simple cylinders, things like pins, rods, shafts, rollers, where you need to grind the whole length.
So super efficient for those kinds of parts.
Incredibly efficient, and you generally get excellent size control and roundness along the whole length.
The table summarizing the differences in the materials was really helpful. Infeed for complex shapes, specific forms. Thrufeed for high-volume cylinders. Infeed, wheel moves in. Thrufeed, part moves through. Choosing the wrong one sounds like it would really mess things up.
Oh, it absolutely would. Trying to through-feed a bolt with a head just wouldn't work.
Right.
And trying to use infeed for, say, thousands of simple pins, wildly inefficient.
Yeah, time-consuming.
So understanding which method fits the part's geometry and the production volume you need, that's a fundamental decision.
Okay, so we've hit wheel selection, setup, the work rest blade details, the two main methods. The final piece, but definitely not the least important, seems to be maintenance. Keeping these machines in top shape.
Crucial.
Sounds like proactive care is the name of the game to avoid costly breakdowns and keep things accurate long-term.
That's absolutely right. Think of a centerless grinder as a high-precision instrument. Like any high-performance machine, it needs regular, careful attention to stay accurate and reliable.
And neglecting it.
It's just a surefire way to get unplanned downtime, bigger repair bills, and ultimately parts that are out of spec.
The info you sent breaks maintenance down by frequency, starting with daily tasks. These seem pretty basic: check for damage, keep the area clean.
Good housekeeping, essentially.
Right, prevent grit contamination.
Yeah,
And check coolant levels and condition.
exactly. Those daily checks are your first line of defense. Spotting a loose bolt or bad coolant early can prevent much bigger headaches later. Then you move to more in-depth checks, maybe weekly or monthly. That means looking closely at lubrication systems. Are the auto lubers working? Check levels, look for leaks, blockages.
Making sure everything gets the oil or grease it needs.
Precisely. And it's not just lube oil. The hydraulic system needs checking too. Fluid level, temperature, filters. Inspect the hoses, listen to the pump for weird noises.
And the spindles themselves, the grinding and regulating wheel spindles.
Critical components. Monitor bearing temps, listen for noise or vibration, check for any play, leaks around seals. If they're oil mislubricated, check that system too.
Gotcha. What else in those regular checks?
The truing and dressing units, the things that shape the grinding wheel. Check their ways, make sure they move smoothly, adjust gibs if needed, check the diamonds are sharp and working right.
Keep the dresser accurate so the wheel is accurate.
You got it. And don't forget the basic mechanical stuff: hand wheels, lead screws, bearings. Check for wear, smooth operation. Even a quick look at the electricals, clean motor fans, cabinet filters. Check connections with the power off, obviously.
Right, safety first. Then there are the less frequent, maybe annual or periodic tasks. Sounds like the bigger jobs.
Yeah, the deeper maintenance. Like maybe a full lube system flush and refill, if the maker recommends it. Replacing all the key filters, hydraulic, coolant, maybe air filters.
Getting ahead of problems.
Exactly. Proactively replacing parts known to wear out. And really importantly, a full geometry check and calibration.
To make sure everything is still perfectly aligned.
Precisely. Make sure all the alignments and movements are still within the manufacturer's specs. And finally, it's about continuous monitoring. Just always being alert.
Listening, watching.
Yeah. Increased vibration, weird noises, finish quality dropping off, trouble holding size. These can all be early warnings that something needs looking into right away.
Okay, so pulling it all together, mastering centerless grinding really sounds like understanding how all these things connect.
It really is.
Wheel selection, the setup details, that crucial work rest blade, picking the right method, Infeed or Thrufeed, and then just consistently doing the maintenance. They all influence each other.
Precisely. It's a system. Optimize each part, and the whole operation benefits. Neglect one area, and it can ripple through, causing inefficiency, poor quality, higher costs.
This has been a really, really insightful deep dive. Okay, thinking about that connection between wheel selection and the work rest blade angle. What subtle tweaks there might give the biggest bang for the buck in someone's specific grinding job?
That's a good one. And knowing the differences, the best uses for in-feed versus through-feed grinding, what other manufacturing processes out there could maybe benefit from similar tailored approaches, based on part shape and production volume?
Really interesting things to chew on there. Thank you so much for sharing your expertise today. We certainly hope this deep dive has given you, our listener, a much clearer picture of what it takes to optimize your centerless grinding operations.